I'm actually going over time. Sorry about that. We're going to finish up with the actuators. Control systems drive the spacecraft toward a desired attitude. There are two different flavors, passive and active. Passive control systems act upon the system without any sensory input and take advantage of physics. Some examples of passive systems are passive magnetic damping and gravity booms. Active control systems take an attitude estimate, calculate control input, and actuators execute the control input to drive the spacecraft to a desired attitude. So here's that representation. For passive actuators, we've got magnetic damping and gravity booms, which we talked about last lecture. In this lecture, we're going to be talking more about the active components, like magnetorquers, reaction wheels, control moment gyroscopes, which are like fancy reaction wheels, and thrusters. So, magnetorquers. Not only can we sense magnetic fields, but we can also impose a magnetic field to get some kind of resultant force or torque. So, I do have a problem with this picture here. This diagram says resultant force, but given that your satellite is in space and it doesn't have anything to leverage against to exert a force, that force would just be translated into a torque. So in the larger context, let's see, this question, my answer is going to address this question. Do these methods draw the CubeSat minutely closer to the Earth and shorten its orbital life? So if the magnetorquers could exert a force and change the velocity of the spacecraft, then it certainly is the case that you could be elongating or shortening the CubeSat's mission lifetime. But because that force translates into a torque and all of that force gets translated into a torque, then the CubeSat, in fact, its orbit does not change at all, only its attitude. Why? That's a question. Why were embedded torque coils chosen for Artemis as an active control system? To save on space? Nailed it. Yes, absolutely. So magnetic torquers can come in different forms. There can be these electromagnets that look like hot dogs, and they look like rods. They're tightly wound coils, like so, or they can come in these more hockey puck shapes or hamburger shapes where it's a flatter, wider coil. So what we've done, we've embedded, well, Kalai, shout out to Kalai, embedded coils of copper wire within the solar panels, within a printed circuit board that are going on the faces of the Artemis CubeSat kit. So yeah, I think it was an ingenious save on space so that we don't have to have dedicated rods that are taking up volume within the CubeSat volume itself. So I think these equations should be very familiar to you, where the electromagnet or the magnetic dipole you're creating from this coil is equivalent to the number of turns times the current that you're running across it in the amperage, amperage inductance. Oh my gosh, I'm sorry. I is the current and A is the area. So number of turns, current, and area of the coil. And then for the amount of torque that is applied, remember torque is in 3 degrees of freedom, so it's a vector. It would be your magnetic dipole crossed with the local magnetic field. This is a table of specifications that you would see for a magnetorquer. That should get you this equation, this value that you want to see. Okay, so reaction wheels. Reaction wheels are rotors that spin. They're usually put in a housing, so you'll see this covering, and they usually come in packs. So you can have one reaction wheel if you, for example, just want to control one axis, like you're seeing here. But in 3 degree of freedom systems, you'll see these configurations where these 3 are orthogonal or linearly independent from each other, or you'll see these arrays that are in 4, so there's one redundant, and you need to use a combination to get different directions of control. Control moment gyroscopes are these spinning rotors, but they have one additional axis that it can spin about. So you'll see here that here is the reaction wheel, but it also has this axis that it can pivot about. Instead of changing its speed, it just changes the direction of the angular momentum from that rotor, and that can create a torque on the system, as you're seeing here. The International Space Station uses 4 of these, and here's a depiction of how it works. So yeah, we're talking about the rotor. It has some angular momentum from its spinning, and it imparts a torque by changing the direction of the angular momentum vector. I have a special love for them because I used to work on them, but they are mathematically difficult to wrangle. Okay, so thrusters, something that you'll see on the space shuttle and other command capsules, command modules, like here, they usually come in packs, and they usually are located in corners of spacecraft. So they work by exuding exhaust gas from a thruster. So that imparts some kind of linear momentum to the system. But if they're at a corner, if they're offset from the center of mass or center of rotation, which are one and the same, then it can impart a torque on this body. So yeah, that was a thruster test. Cool. So actuator design, much like sensor design, you want to think about the degrees of freedom that you need to control. You can have a combination of the different actuators that I talked about earlier. Very commonly, you'll see magnetorquers. I'll back up. So there are sources of internal torque, like reaction wheels and control moment gyroscopes. And there are sources of external torque, where you're interacting with the environment, like magnetorquers and thrusters. You usually want to have a combination methods of not only exuding internal, but also external. And then when choosing specific combinations, maybe you want to think about the scaling of particular actuators. So magnetorquers, they scale down pretty well, but scaling up not so well, whereas reaction wheels are the opposite. They don't scale well down, but they do scale well up. Control moment gyroscopes, for example, the ISS, huge, and that's why you would use control moment gyroscopes. Here's a question. What size would be the smallest configuration of a CubeSat to be able to still use reaction wheels for control? Here I have shown a half U package for an ADCS system. So there are 2 cameras. You can use either for Earth or for Sun. And then here are the little cube wheels that come with it. So hopefully that gives you some length scale for reference. These cube wheels can be very small and fit within our 1U, but if we have this whole package, it would take up half the volume, which does not give us much freedom for our payload and all the other supporting electronics that we need inside. Okay, we made it. Uh,